Hi there. Welcome back. It's been a little while. Thought I'd let you try to catch up. Once again, this book is very condensed. I'm not necessarily happy with section 10.3 right now, but I'm going to proceed ahead. The way this book is sectioned out, we may actually make it to the end quickly, like maybe 2 weeks before we're supposed to be to the end, and then we may create some kind of extra review exercises. But for right now, we're going to proceed forward and try to get, basically the department requirements done, which is let's get our MMLs worked out for all trig sections in this book. Well, anyway, here's section 10.4, inverses, lecture 1 of, I don't know, there's a lot here. So we're going to do a review of inverses in general to start with. So mostly, or most people say, what is an inverse? And they reply, switch x and y. That works great. Let's do it. So if I give you a line, y equals 2x minus 3, and you switch x and y. By the way, this is also called f of x. We know a line is a function because it passes the vertical line test. And then you add 3 and you divide by 2. You can do it slightly, or you can just divide both sides by 2. I'm going to divide each individual term by 2. I get y equals 1/2 x plus 3/2, and we call that f inverse of x. Now, I'm going to choose an alternative way to regenerate this right here. First, I would like to graph the original function. Was it minus 3? Minus 3. Y-intercept, negative 3. Up 2 over 1. Up 2 over 1. Up 2 over 1. There's the graph of f. Now f inverse has a y-intercept of 1.5, and you go up, let me see, up 1 over 2, up 1 over 2, and this is f inverse. Inverses are very easy to graph, assuming you can graph the original function. Maybe you'll recall that inverses fold about the line y equals x. If you don't, that's fine also. Now, what I'd like to get at is if I started this from scratch, you can see that if the original equation is a line, then the inverse is a line. So if you're given f of x to be 2x minus 3, what is the y-intercept? Well, the y-intercept is 0, negative 3. Look right there. And we know the x-intercept is add 3 divided by 2. Additionally, we know the slope of the function f is 2 over 1, which is delta y over delta x, as we learned in Algebra 1 class. Now, if you switch the x's and y's, in inverse land, you get the x-intercept negative 3, 0. You get the y-intercept 0, 3/2. You get the slope 1/2. And since I know it's a line, the equation has to be just like we had above. Remember, it is as simple, or can be as simple, as switching the x and y's. By the way, I had pneumonia for about 10 days, so it was not good. Maybe I sound like I have a cold, but I'm telling you what, I feel way better than I did. just 10 days ago. That's part of the reason why I haven't been communicating much. Wasn't feeling great, that's for sure. Well, anyway, there's more. I would like to look at f composed with f inverse of x. Slang f circle f inverse. Technically, composition, I don't like the circle notation. I would just wish they would write it down as is. That's composition. Now, maybe you know this, maybe you don't, but we will attempt this. So if we have our f, and we take our inverse from above, then we got to slap this into f of x. I'm going to write down f of x right here. But before we do that, let's warm up. F of 1, 2 times 1 minus 3. F of 2, 2 times 2 minus 3. F of smiley face, 2 smiley face minus 3. Almost there. I got to do these warm-ups. F of crap, 2 crap minus 3. What is this? Well, this is a bunch of crap. So you go 2 crap minus 3. Anything that's not an x just basically looks like some crap to me. And if you bring it, excuse me, distribute the 2 plus 3 minus 3, you get x. So I did all that work for nothing because inverses annihilate each other. And if f composed with f inverse equals x, you know f inverse composed with f of x equals x. Once again, inverses annihilate each other. All right, there's phase 1 of your algebra review. Next, given f of x equals x squared, we can quickly find its inverse by switching the x and y and isolating y. And you're like, uh-oh, there's 2 answers. Can I have 2 answers? No, you can't. This is f inverse of x, but algebra says I'm going to probably need to cross this off. But let's look at the graph. I know the graph of y equals x squared. Looks like this. 0, 0, 1, 1, 2, 4. Negative 1, 1, negative 2, 4. I can graph its inverse. Flip 0, 0, flip 1, 1, flip negative 1, 0, get 1, flip negative 1, 1, and get 1, negative 1, flip 2, 4, and get 4, 2, and symmetric. I did graph the inverse, but it turns out that this is not a function, and we want it to be a function, I guess. Since we're using f notation, it'd be great that it was a function. So what we're going to do here is we need the inverse of x squared so we can get x by itself, meaning you like to take the square root of x squared and get x. So bottom line, we're going to scribble. And if we scribble here, we actually scribble here. So by scribbling, we got rid of the negative. But when you scribble, you have to account for that, or have to tell people that you're scribbling. So the domain, that stands for domain, the axis of f restricted. All restricted means it's scribbled, is now 0 to infinity. The range of f, not that we care, you're going up to the blue function, starts at 0, and it goes all the way to infinity, 0 to infinity. But note, since the domain of f restricted is the x's, it equals the range of f inverse. And the range of f, restricted or not, the range was 0 to infinity. That the y's are now the x's. So the domain of the function is the range of the inverse and vice versa. Next, when you work with inverses, other weird things can happen, like the function y equals 2 to the x, which we will call f of x. We have, you can make an xy table. Say it's been a while. 0, 2 to 0, 1, 1, 2 to the first 2, 2, 2 squared, 4, 3, 3 cubed. Oops, 2 cubed, 2 times 2 is 2, 8. The tricky one, negative 1, 2 to the negative 1, 1 over 2 to the first, therefore 1 half. Negative 2, 1 over 2 squared, 1 fourth. Exponentials are a great group of functions. Notice that they're positive, meaning above the y-axis. They have a one-sided horizontal asymptote, and they're either increasing or decreasing all the time. These are great functions. I always say, how many points do you need to graph an exponential? And I always say 2. You go 2 to the 0, 1, 2 to the first 2. Therefore, since it has to have a one-sided horizontal asymptote approaching 0, looks like that. Well, anyway, who wants to graph the inverse? The answer is, well, of course I do, because it's just flipping points. So you go 0, 1, you go 1, 0. You go 1, 2, you go 2, 1. And a horizontal asymptote becomes a vertical asymptote. And you can see this is f inverse of x. So it even passes the vertical line test, so it's a function. So this is awesome. You know what we need to do? We need to go find it. So remember, switch x and y. Now I need to get y by itself. So you know what I'm going to do? I'm going to take the yth root of 2 to the y. And therefore I get the yth root of x equals 2. But, man, I need to get that y by itself. So you know what I'm going to do to both sides? I'm going to take it to the y. And I get x is 2 to the y. Now, you know what I'm going to do now? I'm going to take the yth root of both sides. As you can see, I'm in an endless circle. I'm never going to find the inverse. Therefore, you're going to have to let me name it. It exists. I see it. I'm going to call it log little sub 2 of x. Log base 2 of x. It's very, very, very clever notation. This says, I am the inverse of 2 to the x. And since 2 to the x is a joke to graph, therefore log base 2 of x is a joke to graph, because just flip your points. X's are y's and y's are x's. So this time, I just had to make up a name for it. It is actually pretty clever, except for the whole LOG thing. But anyway, there So sometimes you just got to name your inverses. Now, here we go. Sine x. Let's go back to forward 4. Graph sine. Now, I'm going to graph its inverse. 0, 0 becomes 0, 0. Been a while. This is pi over 2. This is 1. Therefore, I'm going to graph 1 pi over 2. This is pi 0. Therefore, 0 pi. Therefore, the graph looks like this. Now, that is not even close to a function. That thing is not good. It does have a name. This is f of x equals sine x. This guy is, well, we don't want to use f inverse of x because it's not a function, but it's said to be capital A arc sine x, or capital S in inverse x. It's kind of old school, but I'm old school, so at least thought I'd mention it. By the way, that is pretty antiquated also. Arc sine is sine inverse, but you should know, it's kind of like angles. They're measured in degrees, minutes, and seconds, and now, they're decimal, but a little history won't kill you. Now, here's what we need to do. We need to make the inverse a function. So what we do is we scribble, and we all got to scribble in the same places. I scribbled out infinitely just about the whole graph. I just got this little segment left. We need the inverse to exist so bad that we're willing to just scribble out 99.9999% of the sine graph. Now, to understand this section, you have to memorize where we scribbled the six graphs. So you got to understand the domain of sine x restricted. You need to memorize that window. Now, it is equal to the range of sine inverse x. And clearly, the range of sine x is -1 to 1, but if you restrict it, it was still -1 to 1 equals the domain of sine inverse of x with a little s. Now, I've been doing math for a long time. Went to University of Lincoln, Nebraska for 5 years for grad school, ages basically 23 to 28. Went to University of Wisconsin La Crosse, math, physics, chemistry, and been doing this for a long time. I have not used the graph of inverse sine. Can I draw it? Sure. Watch this. Here, here, here. Here, let's make it fatter. It's just fun to do. Here we go. Oh, look at that. That's the graph of inverse sine, where this is 1, this is pi over 2, negative pi over 2, negative 1. I haven't had much need for the graph of inverse sine, but there you go. There it is. Now, I need to continue getting the other 5. Now, this page is kind of full, so I'm going to do inverse cosecant. I'm not going to do them all from scratch, but I'm going to kind of give you a quick version of it. So we graph sine, and if you were to graph cosecant, you you flip it over and create those asymptotes at those corresponding zeros. So you know this is pi minus pi 1, -1. And we scribbled restricted, scribbled, same thing, sign to be like that. Therefore, when you want to introduce inverse cosecant, you're going to have to do that. So, for the first time the other day, I was teaching another section of this, and I actually graphed inverse cosecant for the first time in my entire life. I don't know if that's good or bad, but anyway, I can do it. I just don't think it's necessary. This is the point pi over 2, 1, so 1 pi over 2. This approaches a vertical asymptote at 0, therefore this approaches a horizontal asymptote at 0. You take this point here, negative pi over 2, -1, you get -1, negative pi over 2. And it has a horizontal asymptote, a vertical asymptote, therefore this has a horizontal asymptote. And this is the graph of inverse cosecant of x. Once again, really had no need for that. The only thing I need to understand is the domain of cosecant x inverse. I'm trying to create the inverse domain of cosecant of x restricted. Once again, to understand this, you just got to remember the scribble. So it goes from minus pi over 2 to 0, not including 0 because of the asymptote, 0 to pi over 2. A little rusty. Well, anyway, kind of super speed coming up here. I'm going to quickly just show you how to scribble the next 4. Okay, so cosine, we all met at a national scribbling conference, and we all decided to scribble like that, leaving the domain of cosine x restricted to be 0 to pi. And similarly, the domain secant x restricted is basically 0 to pi. Take away the asymptote pi over 2. That's graduate level notation. You probably should call it 0 to pi over 2, not including union, not including 2 pi. That's how you remember where it's restricted. So, tangent and cotangent. I'm telling you, tangent inverse is huge. So tangent, it's just natural, actually both of them, of where to scribble. It's not like there was much to say. Let's just look at this section and scribble out everything else. But you know this distance pi, therefore these are pi over 2's. Those are vertical asymptotes, so if you graph it, they become horizontals. And this is pi over 2. This is minus pi over 2. And the reason I have you memorize the graph to be pi over 4, 1 is so you can graph 1 pi over 4. Flip 0, 0, you get 0, 0, and etc. That is the graph of inverse tangent of x. Where did I scribble it? Well, the domain of tangent x restricted minus pi over 2 to pi over 2. Pretty much like sine and cosecant. And finally, cotangent. I don't even try to relate tangent and cotangent. It just seems like it messes me up. So I just memorized the graph of cotangent. Vertical, vertical, 3 dots there, there, there. Do that. And of course, that's the part everybody saves. They scribble the rest. So this is pi over 2, because I memorized this distance to be pi. I know at pi over 4, it's 1. And I got a pretty good graph. Now, I can graph cotangent inverse just as well as I can graph tangent inverse. It's just that the question about cotangent inverse never comes up. But if it did, all you do is say, I got verticals at 0 and pi. Now I have horizontals at 0 and pi. And then you plot your 3 points. Boom. So pi over 4, 1. 0, pi over 2. So pi over 4, okay, okay, here we go. 1, pi over 4. Well, that's tricky because this is pi over 2. This is pi. And negative 1 is okay, here we go. So this becomes 3 pi over 4. Negative 1 becomes negative 1. 3 pi over 4. Wow. I don't think I've ever graphed this in my life. Sorry about being slow. It's kind of cool. Kind of cool. All right. So after all that, I could have just told you this. Could have just skipped the whole 27 minutes previous to this. You remember 1, 2, 1, 4, that would be. But you got to remember minus pi over 2 to pi over 2. Your angles can only lie in here. And that works for sine inverse, cosecant inverse, and tangent inverse. You must memorize cosine inverse, the scribble associated with it, secant inverse, and cotangent inverse were from 0 to pi. They can only lie in there. Now, when I write trig, I mean any of the 6 trig functions, sine, cosine, tangent, secant, all those stuff. Okay, theta equals some number. Now, the numbers that you go sine of are in the domain of the trig. The answers are in the range of the trig. And you should be able to draw all 6 graphs and look at the graphs and tell me the domain and ranges. But here's the deal. If you trig inverse trig theta equals trig inverse of a number, you know inverses annihilate each other and you get theta equals trig inverse of number. Well, this is the domain of trig inverse. And this is the answers trig inverse. And that is very important because these mnemonic devices right here and here are basically your answer space for inverse trig problems. So here we go. Okay, so if somebody asked me sine inverse a negative 1/2 equals theta, because it's sine inverse of a number equals an angle, this is the range of inverse sine of x, which is quadrants 1 and quadrants 4. But the weird one, you can only give me answers from minus pi over 2 to pi over 2 or minus 90 to 90. But it, like negative 45 does lie in the fourth quadrant. Well, anyway, I'm going to take sine of both sides. And I get negative 1/2 equals sine theta. Now, I'm really good at this because I'm a master of the unit circle, but sine, all students take calculus, is positive, positive, negative, negative. So sine is negative in the third and in the fourth. Therefore, 1 dot high, 2 dot low, theta is in the fourth. Now it just comes down to, did you memorize this? When does sine theta equal 1/2? Well, it's 30 degrees. So, or look it up in a unit circle. So this is 30 here, and this is 30 here. Therefore, that'd be 210 and 330. So everybody and their mother wants to say the answer is 330, but you can't say 330. You got to say negative 30 after all that. So the answer is negative 30 degrees. Oops, maybe we should work in radians, minus pi over 6. See how that's done? Boom. When you're working with inverses, always be cheating in degrees. Switch it to radians, or at least do it in degrees first and then switch. I kind of tease that you should always work in radians, but I'm telling you, when you do inverse of a number, you better be thinking degrees. It'll help you a lot. Okay, we're doing pretty good. Getting close to like a whole ton of examples here, but I'll do a couple more low level, and then I'll end this lecture, and then I'll have a full lecture of just me working problem after problem after problem after problem. So here we go. Cotangent inverse of negative the square root of 3. Now, we don't even have a cotangent inverse button, nor am I actually using the calculator during this lecture, but I will in the next lecture. But you got to understand that equals some theta. Now, cotangent inverse is memorized to be quadrants 1 and 2. This angle lies in 1 or 2. But I take cotangent of both sides, and I get minus the square root of 3 equals cotangent theta. But cotangent is like tangents, and all students take. These are the positive quadrants for tangent and cotangent. Therefore, it's negative here and here. So I got a first and a second, and I got a second and a fourth. Therefore, 1 dot high, 2 low, theta is in the second. So I know my unit circle really well. I know my tangents are 0, square root of 3 over 3, 1, square root of 3 in D and E. But I also know my cotangents are and I see the square root of 3 corresponds to 30 degrees. Therefore, if I'm in the second quadrant, I know this is 30 degrees. Therefore, I'm looking for a 150 degree angle. So the answer is 150 degrees. Or pi over 6 is 30, 5 pi over 6. Once again, right now you know enough just to be dangerous. Let me end this lecture, fire up go right into the second one, and we'll get through this section. This section is kind of in our way. I'm glad to get it out of the way early here. It allows us to jump into vectors, which are really basically, maybe they won't seem trivial to you, but vectors are really nice. Law of sines, law of cosines. So it allows us to get into some trivial material, which is nice. I know that last section was a Lulu, and I'm not even promising we're done with that section. Anyway, section 10.4, very important as far as I'm concerned. It helps you understand trigonometry. And it basically helps you memorize your graphs. And, you do have to memorize where you're scribbled to do inverses. Anyway, that's it. See ya.